All right, welcome to topic number 23, rational functions and asymptotes. So this topic and the following topic, I'm going to begin to show you how to graph rational functions by hand, okay? So the first thing we're going to learn is what's so-called asymptotes. All right, so just quickly recall, a rational function is actually a function that can be expressed as P over Q, where P and Q, okay, both numerator and denominator are polynomials, all right? And you remember that the denominator can never equal to zero. So when we talk about rational function before, we mentioned that something called the restriction on the domain. To find the restriction on the domain, you have to set the denominator not equal to zero and solve for x. So those restrictions on the domain, there's actually two different kind. One of them, I think I already mentioned it, is actually a hole in the function, okay? A hole in your graph. So that hole only occurs when a factor of numerator and a factor of denominator can cancel out. That's where the hole is going to occur. The other type of restriction on the domain is actually called the vertical asymptote. Okay. So you have two types of restrictions. Before I just called them restriction on the domain. All right. So now I'm gonna kind of to be more specific. One type of restriction is called the vertical asymptote. The other one is a hole in your graph. All right. So basically, a vertical asymptote is a vertical line that divides the rational function or your graph into different parts. So to find the vertical asymptote, first thing you do is factor both numerator and denominator of your rational function. Reduce or cancel out the common factor in a numerator and denominator. So here I make a quick note. Any common factor that were canceled are actually the holes in the graph. Okay, so that you got to keep that in mind, especially you got to keep that in mind, especially when you begin to write out the domain of your rational function. All right, number three, set the remaining denominator, whatever is not canceled out, okay? You might not cancel every time, but whatever is not canceled out, set the remaining denominator equal to zero, and then solve for the variable. And whatever x you solve, that will be the vertical asymptote. All right, so I'm gonna turn on my calculator here. I'm gonna graph here in a minute. All right, for example, okay, consider the following rational function, factor the rational function. All right, so number one, I need to factor. So x plus 7 on the numerator cannot be factored other than 1. So I'm going to go ahead and put them in the parentheses. To demonstrate, I already factored it. Denominator x squared minus 49 is actually a difference of squares. So that should give me x plus 7, x minus 7. All right, number two, reduce any common factors. So the common factor that can be canceled out here is your x plus 7. So now the function, oops, will look like, since there's no more numerator, once the numerator got canceled out, it becomes a 1. So that's 1 over x minus 7. Number three, set the remaining denominator equal to 0. All right, number four, solve for the variable, move the negative 7 over, x equal to 7. So this x equal to 7 is my vertical asymptote. State the domain of the function. So one of my restriction is the vertical asymptote. The other one is the hole. So the hole occurs, what the factor that I canceled out was x plus 7. If I set it equal to 0, solve for x, then I will know exactly what the hole is. Okay, so there's actually going to be a hole in my graph at x equal to negative 7. Can't see it on the graph, but it's there. Okay, it's actually there. You just can't really see it. So my domain should be, all right, let me graph it real quick. So I'm gonna graph my original function. So x plus 7 is two terms representing one numerator. So I put them in the parenthesis, divided by denominator is x squared minus 49, put in the parenthesis. So this is what my rational function looks like. I'm gonna shift a little bit to the right. Okay, I'm gonna shift it a little bit to the right. I'm gonna extend my x maximum to 15. Shift my graph over a little bit. All right, so this is what my function looks like. So if I actually, so this side is actually keep on going to the left side, and this part will actually stay right below it. Okay, this side, the other part is actually gonna be right. It will keep on going to the right. Okay, it will stay right above it. So I'm gonna take a picture of this graph. I'm gonna show you. All right, so this part keep on going to the right, right above it. This side is stay right below the x-axis. Okay, and there is a vertical asymptote. 1, 2, 3, 4, 5, 6, 7, right here. The graph does not touch the restriction or the vertical asymptote. You can never touch it. So there's actually a vertical line right here, x equal to 7. That's your vertical asymptote. So as a function keep on going to the left, 1, 2, 3, 4, 5, 6, 7, there's actually a hole right here. One, two, three, 4, 5, 6, 7. There's actually a hole right here. Okay. Stay right below it. So my domain got to be from left to the right, from negative infinity all the way to my hole, negative 7. Okay, since my graph does not exist there, so I could use a parenthesis, right? It's not on the line. Union from negative 7 to the vertical asymptote, my function does exist. And my function can never ever touch the vertical asymptote. So I have to use a parenthesis also. So this negative 7 is a hole. Well, the parenthesis, I'm gonna kind of write it down. This parenthesis is a hole. This parenthesis is a hole. This parenthesis is for the vertical asymptote. All right, from the other side of the asymptote, my function does exist. So the other part will be from 7 to infinity. Okay. All right, so that's how we actually find vertical asymptote, and that's how we actually find a hole in your function. So if nothing cancels out, then there's no hole in your function. All right, let's take a look at horizontal asymptote. Horizontal asymptote, you know, every rational function has a horizontal asymptote, but you don't see those. You don't actually see those. How do I know this graph? Okay, actually, one side is actually stay above it, the other part stay right below the x-axis. Okay, how do I know it behave like that? So horizontal asymptote also divides your function into different parts vertically. Okay, vertical asymptote divide your function left and right. Horizontal asymptote divide your function top and bottom vertically. You can think of like that. So let me just come down here a little bit. Um, give myself a little bit of space. All right, so let's take a look. How do I find horizontal asymptote? Okay, this is an imaginary line that nobody sees. This imaginary horizontal line nobody sees. So the way we identify horizontal asymptote, this horizontal line that divides my graph top and bottom, when the numerator and the denominator have the same degree, okay, if the degree of the polynomial for both numerator and denominator have the same degree, then the leading coefficient is the horizontal asymptote. So for example, see the numerator has a degree 2, denominator has degree 2. So when the degree of the polynomial are the same between numerator and denominator, then your leading coefficient, 12 over 4, will be your horizontal asymptote. So when we describe horizontal asymptote, we always say y equal, because that's the equation for the horizontal line, 12 over 4. Your leading coefficient become your horizontal asymptote. 12 over 4 is actually equal to 3. So if I graph this function, I'm going to put 12x squared in the parentheses. I know it's only one term, but I just feel safer to do it. Divided by 4x squared plus 1. I'm going to go back to standard window. Oops. All right, so technically there's a horizontal line right at y equal to 3. Okay, right at y equal to 3. And my function does not go above it. Take a picture of this. All right, one, two, three. It's right about here. So horizontal line kind of bound this graph, right? Okay, there's a horizontal line right here, y equal to 3, right above your graph. Okay, right above your graph. All right, when the degree of the numerator, okay, another scenario, when the degree of the numerator here is 1 is less than the denominator, then the x-axis or y equal to 0 is the horizontal asymptote. Okay, so degree of the numerator is less than degree of the denominator. Then the x-axis, or most of the time I say y equal to 0, is actually your horizontal asymptote. So if we go back to the example I did at the beginning of the class here, right here. All right, you see this is x plus 7, right? Degree is 1 on the numerator, degree is 2 in the denominator. When the numerator is less than the denominator, then x-axis or y equal to 0 is your horizontal asymptote. So that's why here, okay, here, the entire x-axis, this entire x-axis is actually the horizontal asymptote. One part of your graph stays above it, the other part stays below it, okay? Now, how do I know that? Well, I'll tell you that just in a minute, When the degree of the numerator is greater than the degree of the denominator, then there's no horizontal asymptote. Okay, so how did I know my rational function, okay, earlier, one part stays above, one part stays below? Well, we can actually determine mathematically whether and where the rational function cross or don't cross the horizontal asymptote. All right, so we know the graph can never cross or touch the vertical asymptote, but your function sometimes will cross over, will cross over, or you can touch the horizontal asymptote. All right, function cannot touch vertical asymptote, but function can cross or touch horizontal asymptote. So to determine mathematically whether or where the rational function crosses the horizontal asymptote, we're going to set the entire rational function equal to the horizontal asymptote and solve for x. So the example I have an example right here. Let's take a look. First thing we're going to do here is identify the horizontal asymptote. All right. So right now, the degree between the numerator and denominators are the same. Both are 3. So your leading coefficient, 6/2, which is 3, is your horizontal asymptote. So your horizontal asymptote, you will say the equation of the horizontal asymptote is y equal to 3. All right, so demonstrate mathematically whether the function or not will cross or not. So what you do is you take your entire rational function, set it equal to the horizontal asymptote, which is 3, and solve for x. All right, so here I think using cross product will be quicker. All right, 3 times those two terms down there should give you 6x to the third, oops, plus 15x squared. All right, 1 times those two terms up top should be 6x to the third minus 10x. So as you can see, I got positive 6x to the third on one side, another positive 6x to the third on the right side. All right, so they should automatically cancel out. So now what I end up with is 15x squared equals to negative 10x, which will actually make this into a quadratic equation. So I'm gonna, since my x squared term is positive, I'm gonna move my negative 10x over. So that should become positive 10x equal to 0. I'm gonna factor out a 5x. So that leaves me with 3x. That leaves me with 3x plus 2. Set each factor contains the variable equal to 0. Solve for x. So this is gonna divide both sides by 5. This x is equal to 0. Move the 2 over, divide both sides by 3. So this is gonna be negative 2/3. Okay. So right now, your function will cross your horizontal asymptote at these two places. Okay. So if I grab this function, you're not gonna see the horizontal asymptote. Nevertheless, see where they're crossing at. You know what I'm saying? If you cannot even see this horizontal line on the graphing calculator, then how would you know where they're crossing at? So this is how we demonstrate mathematically whether or not the function crosses the horizontal asymptote. And if it does cross, we know exactly where they're gonna cross it at. All right, another type of asymptote is called slant asymptote. Okay, a slant asymptote will occur when the degree of the numerator, okay, is bigger than the degree of the denominator, but specifically, if it will only occur when the degree of the numerator is 1 greater than the degree of the denominator. Okay, this will only happen, all right, if the degree of numerator is 1 greater than the degree of denominator. So this example I gave you earlier, okay, if the numerator is 1 bigger than denominator, that means it's actually considered as our third scenario. Our third scenario says when the degree of numerator is greater than the denominator, then you don't have a horizontal asymptote. That is true. But if it's only 1 degree higher, now here is 2 degree higher. If it's only if the top is only 1 degree higher, then we actually got ourselves a horizontal asymptote. Excuse me, a slant asymptote, sorry. If it's one greater, we get slant asymptote. And to actually find the slant asymptote, we have to use long division. Okay, we have to use long division to find it. So let's try it. Okay, let's try it. So we went over how to find long division before. Okay, so here we're gonna try it again. So before I write it out, my long division, I want to check for missing terms. So apparently my numerator is actually missing 0x squared and 0x. My denominator is 2 power, 1 power, and no power. So I'm missing the constant term. So I'm gonna just say you're missing a 0. So divisor is 1x squared plus 2x plus 0. The dividend numerator is 1x to the third plus 0x squared plus 0x plus 1. So here I will do 3 terms at a time. So my first quotient should be on top of the 0x. All right, first term on the outside, go into the first term in the inside. First term on the outside, go in the first term in the inside, only 1 time, right? 1 times 1 is 1, put below 1x to the third. 1 times positive 2 is positive 2, put below the second term. 1 times 0 is 0, put below the third term. Long division, we will subtract. First term should always cancels out. 0 minus 2 is negative 2. 0 minus 0 is 0. So now I only got 2 terms in the inside, so I got to bring down the last term. 1 going to negative 2 is negative 2 times. Negative 2 times 1 is negative 2. Negative 2 times positive 2 is negative 4. Negative 2 times 0 is 0. All right, once I subtract, first term should cancels out. 0 subtract negative 4 is positive 4. 1 subtract 0 is positive 1. When you look up to the top, your first quotient is lined up with the x's, right? With the x column. So technically, my answer, if we write out the answer correctly, is quotient x minus 2 plus the remainder over the divisor, the original divisor. But it turns out as this horizontal line goes on, okay, to positive and negative infinity, your remainder actually don't matter as much. Your remainder actually don't matter as much. Okay. So the only part I need is actually in the front. It's only the quotient I need. So this slant asymptote will be y equals x minus 2. All right. So I'm going to try to draw a picture for you. And we'll take a look. X to the third plus 1 divided by x squared plus 2x. A little bit complicated here. All right. Y equal to x minus 2. It's a straight line. It's actually a linear function or linear slanted straight line. I want to go ahead and point out when x equal to negative 2, y value is error. All right, because this slanted line y equal to mx plus b. The y-intercept is at y-intercept. Sorry, y-intercept is at 0. Y-intercept is at 0 comma negative 2. Okay. So when x equal to 0, you see there's an error. So your function actually never exists at when x equal to 0, which is your entire y-axis. So it's actually another part of this picture. You know what? There's actually another part right here. So let me go down a little bit. Okay. Go down a little bit, my window to the left a little bit. So I'm going to go to negative 15 for both x minimum and y minimum. See, there's a part right here. There's another part goes up that way. And you can almost see it. It's kind of there. There's actually a line right here. 0, negative 2. It's actually a whole slender asymptote right here. So this side right here doesn't cross it over. The side down here doesn't cross over. Okay, stays where they supposed to stay at. Stays on either side of the slant asymptote. And this slant asymptote is y equal to x minus 2. All right. Don't worry about the remainder. Remainder it becomes insignificant as the function keep on going to positive infinity and negative infinity. All right. So just real quick, showing you how to find the vertical asymptote, horizontal asymptote, and slant asymptote. All right. So let's go over the homework real quick. All right. How do you determine mathematically whether and where the rational function cross or don't cross the horizontal asymptote? So you can just copy the answer from here. Set the rational function equal to the horizontal asymptote and solve for x. Number 2, a slant asymptote will occur when the degree of the numerator is 1 greater than the degree of the denominator. All right, you can just copy it from the lecture handout. Number 3, consider the following function. It'll be easier to write down your answers. So I want you to factor both numerator and denominator. The answer will look like this. Reduce the common factor between the numerator and denominator. So whatever you reduced, all right, that is where your whole is going to be. And your function will look like this. Set the remaining denominator equal to 0 for number 3. Then number 4, solve for x. And then you have to say my vertical asymptote is going to be x equal to a number. Okay, you have to say x equal. You have to write out the equation for the vertical asymptote. All right, looking back to the original function, identify your horizontal asymptote. Look at the original function, identify your horizontal asymptote for me. So when you identify horizontal asymptote, you have to say the equation for the horizontal asymptote is y equal to a number. Okay, whatever that number is. But when you enter your answer, you have to enter y equal to a number. All right, I think that's the only question I have on the homework. Okay, so that will conclude this lecture video on rational function and asymptote. In the next video, I will show you how to graph, okay, rational functions.